Welcome to this explainer. Today we're putting on our detective hats to investigate exactly how a modern EV battery manages its own inevitable decline. It's a fascinating engineering marvel. We're zeroing in on the ultimate battery protection strategy, specifically focusing on a critical fault code known as BMS_A067. We're going to see exactly how the car's brain handles the absolute limit of battery capacity loss. So picture this. What actually happens when an EV battery permanently loses a chunk of its capacity? And more importantly, how on earth does the car know about it before you do? Well, before a driver would ever notice a drop in range or performance, there's this invisible medical-grade diagnostic system already working overtime in the background to keep the battery safe. To unpack this whole technological immune system, we'll trace the battery's life cycle across 5 key stages. We'll start with the root causes of attenuation, move into hardware-software collaborative diagnosis, look at key design defenses, check out quality control in manufacturing, and wrap up with strict pre-production validation. All right, diving right into part 1, the root causes of battery attenuation. Let's take a look at our patient, the battery cell, and find the culprits. Our prime suspect here is BMS_A067. Now, when an EV throws this code, it's not just your everyday low battery warning. No way. This is the ultimate, irreversible diagnostic conclusion that the battery's health has fundamentally deteriorated. Within the software algorithm and control logic layer, which is the 4th dimension of battery safety, this is literally the most severe performance degradation and safety protection code there is. This failure is basically a cascading effect across 3 dimensions. First, on a microscopic level, you have a chemical breakdown where lithium ions get completely deadlocked. Then, macroscopically, just a tiny 3 to 5 degree temperature variance can cause massive thermal hotspots. And finally, you get a software math failure, where the calculated state of health diverges from reality, which can give you a dangerously false state of charge on your dashboard. Zooming in on that microscopic level, the battery is aging through 2 main physical traumas. First up is the loss of lithium inventory. As the battery cycles, the SEI layer thickens non-linearly, which permanently traps active lithium ions. Then there's the loss of active material. High currents literally cause microcracking, shattering the internal pathways and physically blocking the lithium channels. It's like a traffic jam with no way out. Now that we know the disease, let's jump into part 2, hardware-software collaborative diagnosis, and see how the battery management system diagnoses this on the fly. This system is incredibly smart about how it handles data. It splits diagnostics into a dual time-scale observer. Basically, it checks the slow variable, the long-term state of health, quietly in the background to avoid high-current interference. At the exact same time, it's doing high-frequency deductions of the fast variable, the state of charge, which is like the fast-paced, real-time heartbeat of the battery while you're driving. But wait, what if you never fully charge or deplete your car? How does it know the true capacity? Enter incremental capacity analysis, or ICA. Even during a slow charge between, say, 20 and 80%, the system uses high-frequency calculus to extract electrochemical peaks. It's basically reverse engineering your battery's true capacity. It's always learning in the background. So what happens if that health drops too low? If the system sees the state of health drop below a hard line, usually 70 to 75%, it takes drastic action. It locks in a permanent fault flag in the memory, completely prohibits DC fast charging, and disables pure EV mode. It essentially forces the car into a restricted limp-home mode to prevent catastrophic thermal runaway. Brutal for sure, but totally necessary. Knowing how severe this is, let's step back to part 3. Key defenses in design, specifically the DFMEA preventative measures engineered right from the start. Look at this number, 1.12. In the design stage, engineers strictly mandate a negative to positive material ratio of at least 1.12. This is a heroic design threshold. By having excess negative material, it physically widens the safety margin and stops dangerous, spiky lithium dendrites from forming during fast charges. It cuts off the failure right at the chemical source. The design also uses a complex rain flow counting model to track cumulative damage over time. It deploys a really graceful degradation strategy. At 80% state of health, you get an early warning. Drop to 75% and you get a moderate warning that smoothly starts stepping down power. Hit 70% and strict limits are enforced. It's all about easing the stress on the aging battery. Of course, a perfect design is completely useless without perfect execution. Let's move to part 4, Quality control in manufacturing, looking at the intense PFMEA checkpoints. Walking down the assembly line, the checkpoints are intense. First, beta rays scan the coating to ensure the thickness is absolutely perfect. Second, electrolyte injection is monitored via strict statistical process control so the cell never runs dry. Third, and this is absolutely crucial, the exact initial capacity and resistance are bound to a barcode and written directly into the car's memory, so the software never starts with a dangerous null value. Finally, every single battery pack gets a 100% end-of-line DC resistance test. Before any car actually hits the street, we have Part 5, strict validation before production. These are the brutal DVP&R clinical trials. The most dramatic trial here is the hardware-in-the-loop test. Imagine this. Right as the car goes to write that permanent battery death code, the 12-volt battery suddenly dies. Boom, power drops at 0 milliseconds, but at 10 milliseconds, a backup hardware capacitor kicks in. It gives the system Jedi-like reflexes to hold power for exactly 50 milliseconds, just long enough to safely save that fault code to the flash memory. When the car wakes up later, it auto-repairs via a checksum. Absolutely incredible. Then there's this vital metric 2.0. If the BMS S67 failure triggers while you're driving, the system has exactly 2.0 seconds of functional safety time. In the blink of an eye, it has to slash engine power to under 50% and disable pure EV mode. And it has to do it incredibly smoothly to save the driver from a sudden, dangerous stall, all while instantly protecting the battery from a voltage collapse. But honestly, the coolest defense isn't even in the car. It's the cloud digital twin. Your car is constantly sending telemetry data to the cloud, comparing your battery's aging curve against thousands of others. If the AI predicts you're heading for failure, it pushes over-the-air updates weeks in advance. Even before you hit that 75% threshold, it quietly dials back your fast charge rate by 15 to 30%, relieving stress before a microcrack even has a chance to form. So, as these cloud digital twins become the standard, it leaves us with a fascinating thought. Will future EVs predict and completely cure their own demise before the first microcrack even forms? We are rapidly moving from just diagnosing battery death to completely outsmarting it. Thanks for joining this explainer, and I hope you walk away with a newfound appreciation for the invisible intelligence protecting the future of our EVs.